Okay, so let me start section. Oops, 1 second. Okay, so let me start section 9.3, or the algebra functions. So I'm going to define some operations on functions pointwise. So first, let me define addition. So suppose I have a function f and a function g. I'll define the sum, f plus g, pointwise as just f of x. The domain of f plus g is just the domain of f intersect the domain of g. I'll define scalar multiplication. Okay. I'll define scalar multiplication in a second. There. Suppose I have some scalar c, then I'll define, and some function f. I'll define c times f pointwise as c times f of x, where the domain okay, where the domain of cf is just the domain of f. I'll define the zero function. Which will turn out to be the same as the additive inverse. As equaling 0, and this will be for all x. The additive identity, the zero function. And I'll define the additive inverse. Okay. Having a little bit of trouble with the computer. I'll define the additive inverse. It's just being the scalar multiple of f with -1. I'll define multiplication of two functions. F and g as f times g is just defined pointwise as f of x times g of x, where the domain of f times g is just the domain of f intersect the domain of g. I'll define the multiplicative identity, the one function, as just equaling 1 for all x. I'll define the multiplicative inverse. Let's say 1 over g. Again, pointwise, as just equaling 1 over g of x, where the domain of g of 1 over g is the domain of g minus the kernel of g. Where the kernel of g is just the set of all x in the domain of g such that g of x is 0. We'll define division f divided by g as just f times 1 over g. And, well, let me just explicitly state what the domain is of f divided by g. It's just a domain of g, take away the kernel of g. Let me define the equality of functions. So two functions f and g are equal if the domain of f is the same as the domain of g, and if f of x is equal to g of x for all x in the domain of, well, let's say f, but they're of course both the same, both f and g. So with these definitions, the set of functions becomes a field. So let's just explicitly write down the field properties. So let's do the closure property for addition. If f and g are functions, then the new function that we've defined, f plus g, is also a function. And we gave it a nice domain. The closure property for multiplication says that if f and g are functions, then f times g is also a function with the domain as specified above. We have the commutative property for addition. So f plus g is the same as g plus f. We have the associative property. Well, let me do the commutative property for multiplication too. I have the commutative property. For multiplication. So f times g is the same as g times f. Again, this is where both f and g are functions. And multiplication is defined pointwise. I have the associative property for addition. So if f, g, and h are functions, then f plus g plus h is the same as f plus g plus h. I have the associative property for multiplication. Which says if f and g are functions, then f times g times h is the same as f times g times h. I have the existence of an additive identity. Raised hand. Okay, once. See if I can find it. 1 second. Let me. Okay. See if I can find a. See how if I can find the hand. Hand. You raised hand. Yes. Well, I guess you can type something there if you wanted to. Okay. Let's try that. Okay. Do you have a question? Yes.
Can you hear me?
Yes, I can.
Oh, that's tight.
So, did you have a question?
Is this going to be on the test?
Will this be on the test? Yes, but what you have to know of this is what we're going to be doing in a few minutes when we actually do examples. And what you'll see is that all this abstraction is what you think you should do. The way you add is you add, the way you multiply is you multiply. Okay? So when I actually do the examples, you'll see that what you really have to know is the examples. Okay?
Perfect.
Okay, then. I'm going to mute you now.
Okay.
Okay. Yeah, so if you have any questions, just raise your hand and I'll be able to do that. Okay. Existence of additive identity. So there exists an additive identity, the zero function. So that the additive identity, a function plus the additive identity is just the original function. And similarly, so this is a right additive identity. By commutativity, it's also a left additive identity. We have the existence of a multiplicative identity. And so there exists, well, that the one function. And so there exists a multiplicative identity such that a function times a multiplicative identity is just the original function. By commutativity, we also have that it is a left additive identity. Okay. 1 second. Okay. Okay, so we also have the existence of an additive, of an additive inverse. So there exists, well, the negative. And so if I have a function f, I can add to it negative f, the additive inverse. That gives me the additive identity, the zero function. And so if you remember, this was the scalar multiple -1 times your function f. And by commutativity, it's also, besides being a right additive inverse, it's a left additive inverse. We also have the existence of a multiplicative inverse. So if my function is not zero, then there exists the reciprocal, which we had defined above. And this is such that, well, a function times this multiplicative inverse is the multiplicative identity, that one function. And by commutativity, we also have that the multiplicative inverse times any function is just the multiplicative identity. And lastly, we have that multiplication distributes over addition. So if I have some function f and some functions g and h, then f times the quantity g plus h is just f times g plus f times h. Besides being a field, besides being a field, it really is a vector space. So let me give you the vector space properties. And these are going to be somewhat similar to the field properties, but not quite identical. The closure for addition, so just like above, if f and g are functions, then f plus g is also a function. And the closure property for multiplication which says as f and g are functions, then f times g is also a function. We have the commutative property for addition. If f and g are functions, then f plus g is equal to g plus f. We have the associative property for addition. Says that if f, g, and h are functions, then f plus g plus h is the same as f plus g plus h. We have the associative property for scalar multiplication. It says that if A is a scalar and B is a scalar and F is a function, then A times BF is the same as AB times F. We have the existence of an additive inverse, additive identity. Oops. And so there exists some zero function such that, well, f plus 0, f plus the additive identity is your function, so it's a right additive identity, and by commutativity, your additive identity plus your function f is your function f. We have the existence of a scalar multiplicative identity. So there exists a number, 1, say that the field in our case is, well, maybe I'll just call it any sort of general field. We have a identity for the scalars, and the scalar multiple of that scalar identity times a function is just the same function. We have the existence of an additive inverse. So just like before, any function plus its additive inverse is additive identity, and by commutativity, we have it the other way around. We have scalar multiplication distributes over addition. So any scalar a and b such that a plus b times the function f is equal to a times f plus b times f. Okay, so those are the vector space properties. So let me do some examples. Let's say on page 367, let me do problem number, let's say 4. F of x equals negative 4x. G of x equals 1 plus x squared. Okay, so it says here in exercises 1 through 14, use the given functions f and g to find f plus g, f minus g, c, f times g, d, f divided by g, e, 2f, f, 3g, g, 2f plus 3g, and h, 2f minus 3g. So let's determine each of those. So f plus g is just, well, f plus, g. You just add them. And that's your answer. E. F minus g you'll just have f and subtract from it g. Maybe I'll write this as a negative 4x minus 1 minus x squared. C. F times g. So you just multiply them. Negative 4x times 1 plus x squared. Maybe I'll multiply this out. You don't need to do, but I can multiply it out. D. F divided by g. So f divided by g is going to equal, well, f divided by g. And that is your answer. E. 2f. So I'll just multiply f here by 2. So I'll get negative 8x. F. Three G. So I'll just multiply G here by 3. So I get 3 plus 3x squared. G. 2f plus 3g. So I'll just take 2f, add to it 3g. And that is your answer. And lastly, h. 2f minus 3g. So I'll just take 2f and subtract 3g. Oops. And so I get a negative 8x minus 3x squared. And that is your answer. And that's it. Okay. So that's how you do all of these first sets of problems. So it's basically what you would think you would do if you're adding or multiplying or dividing or subtracting two functions. Okay. Let's go on to actually another concept, which is substitution. But really, substitution, I mean composition, and composition of two function is just a different name for substitution. So let's recall substitution. So suppose I have y equals 3z squared minus 7z plus 1. And suppose I have z equals 4x plus 3. And suppose I want to substitute z into y. Okay? Then I'll get y equals 3, well, rather than z, I'll put in 4x plus 3 squared minus 7, and I'll substitute 4x plus 3 plus 1. Okay, so that's substitution. So when we do this in functional notation, we'll call this composition. So composition is just substitution in functional form. Okay, so we have here x. Maybe I'll give a little more room. X goes to z, and let's say by some mapping g and z goes to y by some mapping. Then the rule mapping x to y will be denoted by f composed with g. So suppose I have some set x, z, some mapping G from X to Z. We have some set Y and some mapping F from Z to Y. So let G be a mapping from X to Z. And F being a mapping from Z to Y. So let these be rules. Then the rule defined by F composed with G at X is just F evaluated at G of X with the following domain, with the domain of F composed with G as being the set of all X in the domain of G such that G of X is in the domain of F. This is called composition of F with G, and it's read F of G. So note, in general, F composed with G is not the same as G composed with F. Let me give you the identity function. The identity function just maps X to itself. So note that the identity function composed with F is just F, and F composed with the identity function is just F. So let me give you an example. Let F of X equal 3x squared minus 7x plus 1, and G of X equaling 4x plus 3. Then F composed with G at X. Wherever I see an X in F, I replace every X by the formula given by G of X. So wherever I see an X in F, I replace X by 4x plus 3. And so I'll replace X by 4x plus 3. Note that this is the exact same problem that we had from before. We got the exact same answer. The only difference is instead of calling it y and z, I called it f of x and g of x. Of course, these aren't z's anymore. These would be x's, but same problem, and you got the same answer. Okay. So let me do an example. Let's say problem number 18. In exercise size is 15. Compute A. Oh, well, let me write down what f of x is. F of x is equal to 5x minus 2. G of x equals 2 minus x. So A, compute f composed with g. So wherever I see an x in the formula for f, I'll replace x by the formula given by g. So wherever I see an x here, I'll replace x by 2 minus x. This is 5 times 2 minus x minus 2. If you wanted to simplify that, I get a 10 minus 5x minus 2 is 8 minus 5x. Let me do part B. G composed with f. So wherever I see an x in the formula for g, I'll replace x by the formula given by f. So wherever I see an x in this formula, I replace x by 5 minus 2x. So this is 2 minus x, which is 5x minus 2. This gives you a 2 minus 5x plus 2, which is a 4 minus 5x. And that's your answer. Let me do problem 16. F of x equals 4x minus 1. G of x equals 2. So let's compute f composed with g at x. So wherever I see an x in f, I replace x by the formula given by g, which is just 2. So wherever I see an x, I replace x by 2. 8 minus 1 is 7. So in this case, our answer is 7. Do part B. So wherever I see an x in the formula for g, I replace x by 4x minus 1. There is no x. Therefore, the answer is 2. I replaced every x. There was nothing I could replace. Let me do problem number 36, I guess. F of x equals 2 over x minus 1. G of x equals 1 over x squared. In exercises 36 through 39, composed with G. B, G composed with F. Give the domain in each case. So let me do that. So wherever I see an x in this formula for f, I'm going to replace x by 1 over x squared. So this is 2 over 1 over x squared minus 1. Let me simplify this. Let me multiply both sides of my equation by x squared. And so I get 2x squared over 1 minus x squared. Okay. Let me compute the domain of my function. So to find the domain of your function, you set the denominator to 0 and solve for x. Only problem with this is that this is wrong. Why is this wrong? Because you do not use a simplified expression to find domains. Never use a simplified expression to find domains. Always use the unsimplified. So do not do this. Instead, set the denominator of the unsimplified, the one in black, no red, to 0. Set the denominator, there's another denominator, x squared, to 0, and solve for x. So in this case, I get 1 over x squared is 1, cross multiply. Therefore, x is equal to plus or minus 1, or in this case, x is equal to 0. And so, in this case, the domain of, was it f composed with g, of f composed with g, is a set of all x's not equal to 0, nor plus or minus 1. And that is your answer. So I have to remove 3 points, not just 2 points, from the real line for my domain. Let me do part B, which is G composed with F. At X. And so this is equal to 1 second. There it is. Okay, so wherever I see an X in the formula, I'll replace. So wherever I see an X here in the formula for G, I replace X in the formula given by F. So I replace X here by, so this is going to be a 1 over, I replace X by 2 over X minus 1. So this is going to equal, well, 1 over 4 over X minus 1 squared. So this is X minus 1 squared over 4. Okay. Or you could just have left it in the unsimplified form, because you do have to find the domain. And when you find the domain, you set the denominator to 0. Set the denominator to 0. Well, here, this can't be 0 because the only way that something can be, a rational expression can be 0 is if the numerator is 0. So this actually gives you nothing. So the domain in this case is a set of all x's not equal to 1. Okay. Let me do problem number 42. Here it is, 42. F of x equaling the square root of 3 minus the square root of x plus 5. Okay, so in exercises 40 through 45, write the function f as the composition of two functions g and h. So I want to find g and h. So that f is just g composed with h. Well, it turns out there'll be a lot of answers you could give me. So I don't know, let's say g of x is square root of 3 minus square root of x, and h is x plus 5. So that's one possible answer. You could also have g of x equaling the square root of x, h of x equaling, not that, equaling 3 minus the square root of x plus 5. That's another possibility. Or there's a lot of, you could even have g of x equaling x, h of x equaling the square root of 3 minus the square root of x plus 5. Okay, and that could be, obviously that's the trivial, that one would work always. So you could have, almost an infinite number of different answers. Let me do problem number 50. No, let's do, 50. F of x equaling radical x squared plus 1, g of x equaling 4x minus 1. And exercises 46 through 53. Compute A, F evaluated at g of 1. Okay, so if I plug in 1 here for x, I'll just get 4 times 1 minus 4 times 1 is 4, minus 1 is 3. Now I'll plug in 3 here, and so that's the square root of 3 squared plus 1, the square root of 10. And that's your answer. Let me do part B. G composed with F at negative 2. So I'll plug in negative 2 here. Negative 2 squared is 4, plus 1 is 5. And so the square root of 5. So let's plug in the square root of 5 for G. So it's 4 times rad 5 minus 1. And that is your answer. Let me do problem number, let's say 53. So I have the following table of values. 53, negative 5, 4, 3, 2, 3, 2. And I have following. Negative 2, 3, 0, negative 3, 1, negative 5, 3, 0, 5, 1. Okay. So compute A, F composed with G at 1. So I'll look here at G. I'll input 1. My output will be negative 5. I'll treat that as an input for F. The output is 4, and that will be my answer. Okay. Let's do part B, which is G composed with F at -2. So I will input, let me use green. So I'll input -2 for f. The output is 3. I'll make that as an input for g, and the output of that is 0. My answer is 0. So it's something nice and visual. Okay, that really finishes off section 9.3. Let me go on to section 9.4, inverse of a function. So, well, actually, let's just continue with this. Let's just say section 9.4. So inverse functions. Okay, so the idea is as follows. Suppose I have some mapping x to y. I call that mapping f. If I can find a mapping from y back to x, I'll call that the inverse function. So first, let me define some concepts. So a surjective, sometimes called an onto function. So f is surjective if the range of f is the same as the codomain of f. Note that sometimes we call surjective functions onto functions. So what this means is that if, i.e., if f is some function from x to y, then that means that for every y, there exists an x such that f of x is equal to y. Okay. So visually, this means say if we have so this would be a surjective function. Actually, they even go like this. This is surjective. Because there's no extra little pieces here that are left over. Whereas if I had like this, it'd be not surjective because of this guy. So this piece here makes it non-surjective. Maybe I'll put it in a little red. So not surjective because of this extra guy. One-to-one, injective. So an injective, or sometimes called a one-to-one function. So F is injective. If f of x1 equaling f of x2 implies that x1 is equal to x2 for x1, x2 in the domain of f. So for an injective function, maybe we'll do this. This is injective. Whereas this is not injective. Because you have, maybe I'll put this in red. You have more than one object being mapped to the same object. So it's not one-to-one. So we had the vertical line test as a visual sort of way of looking at if something was a function or not. We have the horizontal line test that will tell you if something is injective or not. So suppose we have the graph of a function. Relative to some coordinate system. Then this function here does not pass the horizontal line test if you can find a vertical line, a horizontal line that intersects this curve in more than one location. So this does not pass the horizontal line test. So this means that this is not an injective function. It's not one-to-one. Whereas if I have a curve relative to some coordinate system, and suppose this is the graph of a function, then if every horizontal line intersects this curve in at most one location, then this passes the horizontal line test, and therefore this function is injective. It is one-to-one. So this is a nice visual way of determining if a function is injective or not. So a bijective function also called a one-to-one correspondence, so a function is bijective if it is injective and surjective. So if a function is both one-to-one and onto, then we say that it is bijective. So the first time that you heard of a one-to-one correspondence is when you were in kindergarten, when they lined up glasses of milk and chocolate chip cookie, and you would match chocolate chip cookie with a glass of milk. So you found some bijection between these objects. Okay. Cardinality. So the cardinality of a set is the number of objects in the set. Denoted by card. And it turns out that if a function is bijective, then the cardinality of its domain will be the same as the cardinality of its range. There are just as many objects in the domain as there are in the range. Let me do some examples. Let's say on page 376. Let's say problem number 12. So problem 12, they give us a graph. So in exercises 1 through 20, determine whether the function with a given graph is one-to-one. Well, if I look here at this horizontal line intersects in more than one location. Therefore, this does not pass the horizontal line test. Since this does not pass the horizontal line test, this means that this function is not one-to-one. Suppose I wanted to do this algebraically. So let me show you how to do this algebraically. So suppose that f of x1 equals f of x2. So in this case, this is absolute x, or in this case, these are h's. So suppose h of x1 equal h of x2. So I have absolute x plus 2 equals absolute x 2 plus 2. Okay. Well, in this case, x2 is equal to x2 plus 2, or x1 plus 2 is equal to negative x2 plus 2, because the absolute value is equal to plus or minus. Subtract 2 from both sides, so x1 equals x2. That's good. Distribute the negative inside the parentheses. Oops, well, it's in orange, I guess. That's fine. So negative x2 minus 2. So I get x1 is equal to a negative x2 minus 4. But x1 was supposed to equal x2, so this is a contradiction. So therefore, h is not 1-to-1. And that's what we found previously by just looking at the horizontal line test. Okay. Recall the identity function. The identity function was just defined as mapping x to itself. And so let's define the inverse function. The inverse function will only be defined for surjective functions. Spent some time telling you about surjective functions, about one-to-one functions, so inverse functions. So let f map x to y. Let this be an injective function. Then the function g from y to x is called the inverse function. Of f if f is if f composed with g is the identity function, and g composed with f is the identity function. And this function g is denoted by f with a superscript of -1. So this is kind of a horrible definition or notation, but that's the notation we use. So note, f inverse is not the same as that. F inverse is not 1 over f. I guess you should note that for the definition of inverse, sometimes Other authors require the function to be both one-to-one and onto. We're just requiring that it be one-to-one to be injective. Note the following, that the domain of the inverse function is the same as the range function. So previously, well, yesterday, I was saying that finding ranges of function was difficult, but it's really just the same as finding a domain of an inverse function. And domains are easy. And the range of your inverse function is the domain of your original function. Note also, the inverse of the inverse is the original function. So let me do some additional examples. Problem number 38. F of x equal x plus 7 over negative 3x plus 5. In exercises 25 through 42, find the inverse of the given function, state the domain and range of the inverse function. Okay, so to determine the inverse function, just write y instead of f of x. Then interchange x and y. So wherever I see a y, I replace x. Wherever I see an x, I replace it by y. And now, solve for y. So cross multiply. Bring all y's to one side of your equation to isolate y on one side of your equation. Factor out a y. Divide both sides of your equation by the constant in front of y. This gives the formula for your inverse function. Let me see, what problem was this? So it's an f. So f inverse is equal to 5x minus 7 over 3x plus 1. And that is a formula for an inverse function. Okay, so now let's find the domain of the inverse function. Well, the domain of the inverse function is the set of all x's not equal to negative 1/3, since you do not want to divide by 0. Note, that's the same as the range of your function. But the range of your function, remember, we did this weird thing where we did for these type of functions in front of x in the numerator and denominator, so y was not equal to 1 over negative 3. So y is not equal to a negative 1/3. There it is. And that was how you got that weird, that weird sort of relationship. Let's look at the range of the inverse function. Well, for the range of the inverse function, it was just a set of all y's. So I said, well, I'm not dividing by 0 here, so y cannot equal 5/3. Note that, well, Again, if I just looked at it here, it would say, well, you can't have 5/3. That was the same sort of relation that I'd given you before. But of course, now it makes a little bit more sense, hopefully. Okay, let me do, let's say, problem number 48. No, let's do problem 50. Problem 50. So I have -2, 1/2, 0, 1, 2, -1/2, 4, 0, 4, 0, 5, -2, 6, 4. It says find the inverse function. So to find the inverse function, well, it's easy. All you have to do is just interchange x and y. And voila. Done. Basically, it's just a relabeling. So instead of calling this x, I called it f inverse. Instead of calling it y, I called it x. So instead of calling this x, I call it y. Instead of calling this y, I call it x. And I'm done. So that's my answer. Okay. So that really finishes off section 9.4. Let me go on to section 9.5. So section 9.5 is graphing. So techniques. In graphing. Okay. So the techniques in graphing are well, translations. I can take a graph and without, changing its shape or anything, I can move it from right to left or just straight up and down without any rotating or anything else. So just right or left, up and down, or a combination of moving it right, left, and up and down. So just moving it from side to side and maybe up and down. Okay, and maybe some sort of angle. 2, reflections. I can reflect it about a line, about a point, about an axis. We'll only be looking really about reflection about axes. I can do scalings, where I can squash the graph or stretch the graph. Really just a rescaling of the x or y axis. And lastly, rotations. It turns out that actually we won't be studying in this class about rotations. That will be done in a later class like pre-calculus. So this is done in Math 259, 260, 262. So it's not done in this course. Okay. So first off, let me give you some basic graphs. Some graphs mostly of power functions. So the graphs of power functions. So first, suppose I have, it's supposed to be intersecting the origin, y equaling x to the n, where n is an even integer, where n is greater than 0, and n is an even integer. Okay. Let me look at so it looks sort of like a parabola. So this sort of looks like a parabola. Now, actually there, finally. Now, the bigger n is, the more flat this will become. So it'll become more steep. It'll become flatter near 0, and then much steeper for values of x greater than 1. Okay. Okay, suppose y equal x to the n. Again, a power function. Suppose n is greater than 0 and n greater than 1. And n is an odd integer. Then it has this sigmoidal shape. Again, the larger n is, the more square this looks. So it'll look more square, the larger n is. Next, suppose I want a graph y equaling x to the n when n is equal to 1. Then it just looks like this straight line going at a 45-degree angle through the origin. Suppose I want a graph y equaling x to the n when n is equal to 0. And it's just this horizontal line passing through 1. Suppose I want a graph y equaling x to the n, where n is less than 0 and n is a odd integer. Okay. Or y equaling x to the n, where n is less than 0 and n here is an even integer. Okay. That looks kind of horrible. Let me see if I can get it looking a little bit nicer. Okay, it looks a little bit better. Okay, so that's for an even integer. The odd integer actually looked better. So it should look more like what I drew for the odd integer. Suppose suppose I have the following. So y equaling x to the n. And let's write this as 1 over n. Y equaling x to the 1 over n, where n is greater than 1, and n is a odd integer. Okay. Y equaling x to the 1 over n, where n is greater than 1, and n is a even integer. Okay. I guess that's it for the power functions. The other power functions will be more difficult for me to sort of give you all the different cases. So these are sort of the major ones these are the ones that you must know. And lastly, the absolute value function. Y equal absolute value of x. Looks like a V. Let's recall. The zeros of a function. This is just the same as the x-intercept. Just a new name for it. So you would set y equal to 0 and solve for x. So let's do some translations first. Let h be greater than 0, k be greater than 0, and suppose we start out with y equal f of x. So let me give you the transformation and the result. Okay. Okay, so suppose that I replace x by x minus h, then I'm going to h units in the positive x direction. Okay. Oh, actually, all I have to do is go up here. Yes, there it is. Okay. That was nothing. Okay, so then I'm going to translate h in the positive x direction. Meaning h units to the right. If I do x, replace that at x plus h, I'm going to translate h units to the negative x direction, which is to the left. If I replace y by y minus k, I'm going to translate the k units in the positive y direction. So k units up. If I replace y by y plus k, I'm going to translate k units in the negative y direction, so down. So you notice I'm always going in the opposite. So if it says negative, I go in the positive x. If it's positive, I go in the negative x. Negative, I go in the positive y. Positive, I go in the negative y direction. Okay. So now let's do reflection. Okay. So about an axis. So let's replace x by negative x. Then I'm going to reflect about the y-axis. So if you change the sign of x, you reflect about the y-axis. If you change the sign of y, you reflect about the x-axis. Okay. And lastly, let's do scaling. Okay. So in this case, let me assume here that my number a is greater than 1. So let's replace x by x over a. So then you're going to stretch the x-axis by a factor of a. If you replace x by ax, you're going to compress the x-axis by a factor of a. If you replace y by y over a, you're going to stretch the y-axis by a factor of a. And lastly, if you replace y by ay, you're going to compress the y-axis by a factor of a. Okay, so note, we had given you up here that the graph of y equaling x is just the line having a 45-degree angle passing through. So if you looked at the graph of y equaling mx, then I would just, and let's write this as y over m equaling x. So you would say if m were greater, say m is greater than 0 here, so I don't have to worry yet about changing anything. So you would start out with the graph of y equaling x. Which meant that if you went 1 unit to the x, you'd also go 1 unit in the y. Now, let's look at y over m equaling x. Well, that means that you're going to either stretch or compress the y-axis by a factor of m. And so rather than going 1 unit, you would be going, say, m units in the y. And so that's the idea of a slope. If you go 1 unit in the x, you go m units in the y. And of course, if m is less than 0, then you're going to reflect about the x-axis. So instead of going up, you'll go down. So this gives you the idea of the slope. And if you replace y by y minus k and x by x minus h, then you've just translated your origin to some other point with maybe a different slope now. And so you've just translated these. So now this origin becomes this new point, hk, and you get a new equation of the line passing through that point, which is the point slope line. The point slope form for the equation of a line. So the point slope form for the equation of a line just follows by translations, reflections, and scaling. Okay. So let's do some examples. Let's say on page 385, let's do problem number 5, f of x equaling x squared minus 1. So y equals x squared minus 1. In exercises 1 through 26, stretch the graph of each function by hand and then verify. Oh, well. And so so this means that this is just y plus 1 equals x squared, adding 1 to both sides. So this is a translation of y equaling x squared. You're adding 1, therefore you're going down by 1 unit. So I'm going to take the original y equal x squared, so this is my original graph. Whoops. And I'm going to go down by 1 unit. And that's going to give me y equaling x squared minus 1. And so that's the graph of y equaling x squared minus 1. I've just gone down by 1 unit. This is a little wider than what it should be, but it's the correct idea at least. Okay, let me do problem number 18. Actually, let's see if there's any scaling. That's good. 18. So I have y equals absolute x plus 1. So this is going to be a translation of y equaling the absolute value of x. But in this case, I'm adding 1 to x. So I'm going to go 1 in the negative x direction. So it'll be 1 unit to the left. Okay, so I start out with the original graph, which is the absolute value. And now I'm going to go 1 unit to take this graph and translate it by 1 unit. And so it should look like that. And that's the graph of my function. Okay, so that finishes off section 9.5. Let me go on to section 9.6. So section 9.6. Variation. So direct, or what we call positive variation, So if we say that y varies directly as x, this just means that there exists some constant of proportionality k such that y equals kx. If I say that, say, inverse or negative variation, if I say that y varies inversely as x, that means that there exists some constant proportionality k such that y is equal to k over x. If I have joint variation, well, joint variation is really the same as direct variation. It's just that in this case, we have more than one variable. So if I say that z varies jointly as x and y, then that means that there exists some constant proportionality k such that z equals k x y. Okay, so let me do some examples. On page 390, let's say problem number 2. Let's say problem number 3. The quantity P varies directly as the square root of Q. So that means that P is equal to some constant proportionality K times the square root of Q. In exercises 1 through 20, write the complete statement of the function. Okay. Let me do problem number 20. The quantity P at the point P of x, y varies inversely as the product of the distances of P from the coordinate axes. Okay, so P is equal to some constant proportionality K. The distance from the point P to the x-axis is y. The product of the distances. The distance from the point P to the y-axis is x. And so P varies jointly, varies inversely as the product of these distances to the coordinate. And that is your answer. Let me do problem number 23. Z varies inversely as the square of t and z equals 5 when t equals 2. In exercises 21 through 28, the complete statement of the function, and then use the given information to find the constant of variation. So z varies inversely. So there exists some constant proportionality, k. So that's a k divided by the square of t. Z is so that is the complete statement of the function. Let's find the constant proportionality. So z is equal to 5 when t is equal to 2. 2 squared is 4. Multiply both sides of your equation by 4, so k is equal to 20. So the constant of proportionality is 20, and your complete statement is z is equal to 20 over t squared. Okay. Let me do problem number 44. According to Hooke's law, the force F exerted on a spring is directly proportional to the amount of stretch x of the spring. If a force of 100 pounds, the spring by 8 inches, find the amount of stretch if the force is 75 pounds. Okay, so let's do that. Okay, so by Hooke's law, force is proportional to the amount of stretch, x. So if 100 pounds stretches a spring 8 inches, so k is equal to I can divide each of these by 4, 25 halves. So the force is 25x over 2. Find the amount of stretch if the force is 75 pounds. So 75 is equal to 25x over 2 multiplied by 2. Divide by 25. And so x is equal to 6 inches. And so the amount of stretch would be 6 inches. Let me do problem number 50. Under a constant temperature, $50. The pressure P of a gas is directly proportional I'm looking at the wrong thing. Under constant temperature, the pressure P of a gas is inversely proportional $50, okay, is inversely proportional to the volume V, a volume of 30 cubic feet of gas exerts a pressure of 6 pounds. Find the volume of the gas when the pressure is 9 pounds. Okay, so let's do that. So pressure is inversely proportional to volume. A volume of 30 exerts a pressure of 6 pounds. So cross multiply. Okay, is 180. So P equals 180 over V. Find the volume when the pressure is 9 pounds. So 9 is equal to 180 over V. And so 9V is 180. So V is 20 cubic feet. And that is your answer. And so that finishes off section 9.6. which finishes off chapter 9. So let me go on to chapter 10. So chapter 10 is on radicals. Here it is. Okay. Chapter 10. Radical expressions and equations. Okay. So section 10.1 is on roots. So the square root of 16 is 4, since 4 squared is 16. So this has a understood index of 2. So here's your index, which is your exponent. The same as your index on the other side. Here is your radicand. And your, well, in this case, maybe I'll just call this the base. So the cube root of 8 is 2, since 2 cubed is 8. So let me tell you about the principle nth root. If n okay, if n is an even integer, and if a is non-negative, then the principle nth root of a is the non-negative real number b such that b to the n is equal to a. If n is odd, oh wait, it can't be 1. Then the principle nth root of a is the real number B such that B to the n is equal to A. Okay. So just note that I have not defined this when A is less than 0 and n is a even natural number. So I have not defined negative roots of negative even roots. Okay, so let's do some examples. Let's say on page 407. But I will actually later today define what they mean. Let's do problem number 4. In exercises 1 through 16, find the principal square root of the number. So the principal square root of 225 is 15. Eight. Principal square root of negative 25 is, well, undefined. We will define it later tonight, not at this moment. Say problem number 18. Or, yeah, in exercises 17 through 26, find the indicated roots if possible. So the cube root of 27, 3, since 3 cubed is 27. 39. In exercises 37 through 50, find the value of the radical. The square root of 144 is 12, since 12 squared is 144. 50. 42. The cube root of negative 125 is negative 5, since negative 5 cubed is negative 125. Problem number 50. The fourth root of negative 16. Well, it's undefined since we have not yet defined the fourth root of a negative number. Let me do problem number 51. In exercises 51 through 64, evaluate the expression. Well, the square root is 17 squared. The square root of 17 is that number whose square is 17. Therefore, the square root of 17 squared is 17. Let me do problem 52. Square root of negative 17 squared. The square root of negative 17 is undefined, so undefined squared as well, still undefined. Let me do problem number 66. The cube root of 27. In exercises 65 through 74, identify the number as rational, irrational, or non-real. Since 27 is a perfect cube, then the cube root of 27 is rational. Let me do problem number 67, square root of 18. Since 18 is not a perfect square, then the square root of 18 is irrational. Let me do problem number 69. The square root of negative 25. Since I'm trying to take the square root of a negative number, an even root, then this is not defined. It is not a real number. And so in this case, they want us to say it's not a real number. Let me do problem number 74. And so, minus the square root of 25. Well, the square root of 20, so 25 is a perfect square, so I can take its square root, and then I can negate it. So therefore, this is a rational number. The negation of a rational number. So that finishes off section 10.1. Let me go on to section 10.2. So section 10.2 is multiplication and division of radicals. So multiplying and dividing radicals. Okay, so let's do some examples of this. Let's say on page 414. Let's do problem number 4. A square root of 3 times the square root of 5. In exercises 1 through 24, use the product rule to write the expression under one radical. Okay, so, well, what I notice here is I have the laws of exponents. It says that if I have two numbers and I'm multiplying them, then I just, and I have the same exponent, then I just multiply the bases and put those all to the same exponent. And so 3 times 5 is 15. Therefore, the square root of 3 times the square root of 5 is the square root of 15. Let me do problem number 34. The sixth root of 32 a to the 4 times the sixth root of 2 a square b square c square. And so this is equal to let's multiply. 2 times 32, 64. A4 times A2 is A6. B squared, C squared. Okay. Well, the sixth root of 64 is just 2. The sixth root of a to the 6 is just a, but I could get rid of it could possibly be that I got rid of the sign of a. So it's the absolute value of a times, well, the sixth root of what's remaining, b squared, c squared. And that is your answer. Let me do problem number 28. That's not 34, that's 24. Let me do problem number, let's say 28. Square root of 25 over the square root of 4. Square root of 25 is 5, square root of 4 is 2. So your answer is 5 over 2. Let me do problem number 40. The fourth root of AB divided by the fourth root negative A negative B cubed. Here it says that we're assuming that both A and B have the same sign. Okay, so I have the fourth root of AB divided by, negative times negative is positive, so that's AB cubed. And so I can cancel out the A's. I can cancel out one of the B's. So this is 1 over the fourth root of B squared. Eventually, later, like in a few minutes, we'll be able to simplify this more. We could be able to simplify this more. Let me do problem number 42. The square root of 12. In exercises 41 through 70, simplify the radical. And so I can write 12 as 4 times 3. And the square root of 4 is 2. Therefore, this is equal to 2 rad 3. Let me do problem number 70. Rad 50, 60, 30, 50 times 60 is 3,000 divided by 30 is 100. Square root of 100 is 10. So your final answer is 10. Okay. So, here, wait, let's see. Let me do problem number 97. Rad 25 a to the 4 b rad 49 a cubed, b cubed over rad 144 AB. Okay. So this is equal to, well, let's at least get rid of the constants. 25 is 5. The square root of 49 is 7. Square root of 144 is 12. And so I have here a to the fourth times a to the third is a to the 7. B times b to the third is b to the fourth over ab. So this is equal to 7 times 5 is 35 over 12. I have a to the 7, b to the 4 over ab. So I can do some cancellations here. And so this is just equal to 35 over 12. I can cancel out one of the a's. I can cancel out one of the b's. Oh, and I guess that's it. Oh, no. So now, in exercises 71 through 1, you perform the indicated operation and simplify. Variables represent positive numbers, so I don't have to worry about any negatives. This is 35 over 12. I can write a to the 6 as well, just a to the 6. I can write b cubed as b squared times b. Writing each of these as the product of some perfect square times the largest perfect square factor of each of those. So this is equal to 35 over 12 times the square root of a to the 6 is a cubed. Square root of b squared is b, rad b. And that is your answer. Let me do I guess that's it, really. So that finishes off section 10.2. Let me go on to section 10.3, which I actually use this. So section 10.3, addition and subtraction of radicals. So I can add or subtract like radicals. So long as they're like radicals, everything's nice and fine. So let me go to page 418. Let's say I want to do problem number 3. 5 rad 7 minus 2 rad 7. So 5 apples minus 2 apples is 3 apples. So 3 rad 7. Let me do Problem number 12. 1/2 rad 10 plus 2/3 rad 10. Well, get a common denominator. The common denominator in this case is 6. So let's multiply and divide by 3, by 2, so I get 3 rad 10 plus 4 rad 10 is 7 rad 10 over 6. And that is your answer. Let me do problem number 16. Rad 8 times rad 3 minus 4 rad 6. So 8 times 3 is 24. Let me write 24 as 4 times 6. The square root of 4 is 2. 2 rad 6 minus 4 rad 6 is a negative 2 rad 6. And that is your answer. Okay. Let me do problem number 20. Cube root negative 9. Cube root 72. Cube root 2, cube root 6. Cube root 4. Okay. And so this is equal to well, let me write this is negative 9 times 72 minus 2 cube root of 6 times 4. Okay. Cube root of a negative number is negative. Notice that 6 times 4 is 24, and 24 is just 8 times 3. So let's factor out a factor of 3. So this is going to be 216 times 3 is the same as 9 times 72. The cube root of 216 is 6. The cube root of 8 is 2. Two times 2 is 4. Negative 6 rad 3 minus 4 rad 3 is a negative 10 rad 3. So notice what I had to do here is I had to write everything as like radicals. So I had to do a little bit of manipulation here so as to be sure that I had like radicals. Okay, let me do problem number 23. Two rad 3 minus rad 5, 2 rad 3 plus rad 5. In exercises 21, perform the indicated operation, simplify. Assume that the variables represent non-negative real numbers. So notice that this is the product of the sum terms, and so their product will equal the difference of squares. So 2 squared is 4, the square root of 3 squared is 3, minus the square root of 5 squared is 5. 12 minus 5 is 7. And that is your answer. Okay. So let me do, say, problem number 35. Two rad x minus 3 rad y, 2 rad x plus 3 rad y. So again, note that this is the product of the sum and difference of two terms, so it's the difference of squares. So 2 squared is 4, the square root of x squared is x, 3 squared is 9, the square root of y squared is y. And that is your answer. Okay. So that finishes off section 10.3. Let me go on to section 10.4, which is rational exponents. Okay, come on. Sorry, it's taking a little while to actually move. Okay, come on. What's going on? Oh, here, it finally moved. Okay. So let me go on to section 10.4. Rational exponents. So let's recall what we've done before. A to the first power was A. A to the nth power. Well, A to the, maybe I should, well, say that A to the 0 is 1 if A is not equal to 0. 0 to the n is equal to 0 if n is not equal, if n is greater than 0. Say that. Actually, we had it defined just for natural numbers so far. Even though it's true for any n greater than 0. A to the n was equal to A times A to the n minus 1. And this is for any integer. And we define A to the minus n as 1 over A to the n if a was not 0, and if n was some natural number. So now let's define exponents. And so this will also almost be just sort of a notation more than anything else. So now let's do these rational exponents. So I'll define a to the 1 over n as equaling, well, the nth root of a if a were greater than 0, or if n was a odd number. Next, we define it as 0 if a is 0. I'm assuming, and it's undefined if a were less than 0 and n were an even number. We will eventually define it as just being this. So eventually, well, it's just so in reality, it's just the nth root, a to the 1 over n is just the nth root of a. When we're done defining everything. Okay. Next. So I guess, in other words, a to the 1 over n is just the nth root of a. So a to the m over n is just defined as, well, a the m to the 1 over n, or I can say it's a to the 1 over n to the m. And lastly, and this is for m and n being natural numbers. And lastly, a to the minus m over n is just 1 over a to the m over n. Again, if you have a negative exponent, that just means take the reciprocal, just like what we did from before. Okay, so let me do some examples. Let's say on page 424, let me do problem number 3, 36 to the 1/2. In exercises 1 through 20, write the expression in radical form and simplify. So 1/2 is the same as a radical with an index of 2. But recall when you have an index of 2, we usually do not write the index. It's understood if you don't write the index, that the index here is a 2. Well, the square root of 36 is just 6. And we're defining this as being the principal, even though sometimes when people write this notation, it means something else. But in this case, in this class, we mean that's the principal root. Okay. Let me do problem number 8. Negative 27 to the 1/3. So this is equal to the negative of the cube root of 27. And so this is negative 3. Let me do problem number 18. Negative 128 to the 4/7. So I can either raise this to the power 4 and then take the 7th root, but raising this to the 7th power, to the 4th power is just going to be gigantic. Or I can do it the other way. It says take the 7th root first and then raise it to the 4th power. When dealing with numbers, it's always best to take the root first to make the number smaller and then raise it to a power. Well, the 7th root of 128 is negative 2. To the 4th is 16. And that's your final answer. Let me do an example. Say negative 128 to the negative 4/7. So this is going to be 1 over negative 128 to the positive 4/7, which we know is 16. So if you have a negative exponent, remember to first take the reciprocal and change the sign from negative exponent to positive exponent, and then deal with that. Okay. Let's do problem number 39. X, A plus B, A minus B, B plus C, B minus C, C plus A, C minus A. In exercises 21 through 44, simplify the expression and write the result in exponential form without any radicals in the denominator. Okay, so let's do that. So since I have a base to a power, I multiply those exponents. So this is the product, the sum and difference of two terms. A squared minus B squared. Again, just the multiply out the exponents. Again, multiply out the exponents. I have the same base. So let's add exponents. Notice b squares, c squares, a squares cancel. Assuming x is not 0, I have that this is just equal to 1. Let me do problem number 60. Square root of 5 x cubed y, square root of 8 xy to the 5, square root 10x5 yx3. So this is equal to, well, let's just multiply everything together. 5 times 8, 40. X to the 3 times x, x to the 4. Y times y to the 5 is y to the 6. 10 x to the 5, y to the 3. Forty divided by 10 is 4. X to the 5th divided by x to the 4th is x. Y to the 6th divided by y to the 3 is y cubed. I can write this as 4y squared times y over x. The square root of 4 is 2, the square root of y, assuming that, again, we're assuming that all variables represent positive numbers. Lastly, let's do problem number 69. Cube root x cubed minus 3x squared plus 3x minus 1. Well, luckily, you remember your special product formulas, the perfect cube. And so this is just x minus 1 cubed. Cube root of x minus 1 cubed is just x minus 1. And you're done. So as long as you remember your special product formulas, this is easy. So that finishes off section 10.4. Let me go on to section 10.5. So section 10.5. Rationalizing. Okay, so let's go to page 429.
Professor?
Say, yes.
I'm so
Question.
sorry to interrupt. Well, it's just I have to go pick up someone from work, and I don't want to miss a lecture. I wanted to know how much longer do you think it'll be?
Oh, it will. Well, it'll be it'll be a while longer. But what you'll notice is that I will be taping. This is being taped,
Okay.
so you can hear the tape later. Well, by tomorrow morning,
Okay.
it'll be up.
It'll
So
be
whatever occurs, you can hear it, and also I'll put up the PDF on EducoSoft. So I'll put up the link to both the
I
link and the PDF.
I actually wanted to watch it live because if I
Sure,
have any
sure.
questions.
Yeah,
But
yeah.
are you going to be covering more chapters than chapter
So
10?
you can come back and yes, yes, we will.
Oh, okay. Thank you.
Okay then. Bye bye. Okay, so page 429. Let me do, say, problem number 3. 4 over rad 5. In exercises 1 through 30, rationalize the denominator and simplify. So in this case, when we say rationalize the denominator, what we mean is that somehow I want to get rid of radicals in my denominator. So let me multiply and divide by radical 5. And so I just get 4 radical 5 over 5. So I no longer have a radical in the denominator. Let me do problem number 6. 5 over radical 10. So let me try to rationalize the denominator. Let me multiply and divide by radical 10. So I get 5 radical 10. The square root of 10 times the square root of 10 is just 10. But I can cancel. 5 divided by 5 is 1. 10 divided by 5 is 2. So I just get rad 10 over 2. And that's your answer. Let me do problem number 8. 5 over 3 rad 50. Note, I can write 50 as 25 times 2. The square root of 25 is 5. I can cancel the 5s. Get 1 over 3 rad 2. So to rationalize, I'll just multiply and divide by rad 2. And so I get rad 2 over 3 times 2. So rad 2 over 6. Okay. Let me do problem number 10. 4 over the, no, I'm sorry, 3 over the cube root of 3. In this case, I don't have a square root, but I have a cube root. So I want to find some number such that if I multiply it, I now have a perfect cube in the denominator. So I'll want to multiply and divide by the cube root of 9. Because I already have 1 power of 3. I want 2 more powers of 3 to make it a perfect cube. So this is going to be 3 cube root of 9 over the cube root of 27. But the cube root of 27 is 3. and the 3's cancel. And so you just get the cube root of 9. And that's your answer. Let me do problem number 30. The cube root of 12 over 25 times the cube root of 2. And so 2 times 12 is 24. I can write 24 is 8 times 3. The cube root of 8 is 2. "25" is 5 squared. So to get a perfect cube, I just need one more power of 5 to make that a perfect cube. So this is equal to 2 cube root of, well, 3 times 5 is 15, over the cube root of 125, which is 5. And that is your answer. Let me do problem number 42. And exercises 41 through 65, rationalize the denominator and simplify. So in this case, I have the sum of two radicals. To get rid of it, I'm going to multiply by the conjugate of the denominator. Which will be just the same denominator, but you'll change the sign of what's in the middle. And so, in this case, I'll be multiplying by radical 5 minus radical 3. Okay, so let's do that. So I have a 3, oops. I have here a 3 over rad 5 plus rad 3. So let's multiply and divide by rad 5 minus rad 3. And so I just have multiplying the 3 inside the parentheses, 3 rad 5 minus 3 rad 3 over the square root of 5 squared is 5. The square root of 3 squared is 3. I have 3 rad 5 minus 3 rad 3, all divided. And notice that I have rationalized the denominator. Let me do problem number 63. Rad x plus 2 rad y over rad x minus 2 rad y. So let's multiply by the conjugate of the denominator. rad x plus 2 rad y, rad x plus 2 rad y. So, by the special product formula, rad x times rad x is just x plus twice rad x times 2 rad y. So that gives you a 4 rad xy plus 2 times 2 is 4. Rad y times rad y is y over, well, rad x squared is x minus 2 squared is 4. Rad y squared is y. And that is your answer. So in general, we actually don't usually rationalize denominators, but we actually usually rationalize numerators. So let me say something about that, rationalizing numerators. So suppose I have the following. Rad a plus h minus rad a over h. And suppose I say to rationalize numerator. So in this case, we don't like the fact that there are radicals in the numerator. So we'll multiply and divide by the conjugate of the numerator. So this will equal, well, the product of the sum and difference of two terms is the difference of their squares. So a plus h minus a over, well, h rad a plus h plus rad a. A's cancel, so you just get h over h rad a plus h plus rad a. The h's will cancel. And so you get 1 over h plus rad a. And that's your final answer. So here, it's actually preferred radicals in the numerator, and you have radicals in the denominator. So it's sort of a preferred thing. So that really finishes off section 10.5. Let's go on to section 10.6, which is equations with radicals. Okay, so radical equations. Okay, so let's do on page 435. Let's do some examples. So it just says in exercises 1 through 64, solve the equation. So let's do problem number 3. The square root of x is equal to 4. So let's square both sides of my equation. Get rid of the square root. So the square root of x squared is just x. Square root of 4 is 16. But what I have to do is check that this is actually a solution. The reason that I must check is because there's a 50-50 chance that I'm actually incorrect. There's a 50-50 chance that I'm wrong. And so in this case, the square root of 16 is 4. So that works. So 16 is actually a solution. But it's still very possible that this technique will give you an incorrect answer. So let me do problem number 8. So whenever doing these examples, you must always check. If you don't check, you'll get half points off because, well, there's a 50-50 chance that you're wrong. So let me do problem number 8. Radical 4a plus 5 equals 2. Subtract 5 from both sides. Square both sides of your equation. Get rid of the square root. And solve for a. So a is equal to 4 over 9, but I better check that 4 over 9 actually works. So radical 4, by the way, of course that doesn't work because 9 over 4. So let's check if 9 over 4 is a solution. The 4's cancel, so it's the square root of 9. But, well, the square root of 9 is 3. And 3 plus 5 is not equal to 2. So this is not a solution. So in this case, since this was the only possible solution, we have that this equation has no solution. This is what's called an extraneous solution. It's a solution to the technique, but not a solution to the actual problem. But notice, if I change the sign of this to a negative, it would have worked. So if the only reason that you're wrong is a sign error in the square root, then well, let me say it the other way, that if it's not a sign error that makes this check not work, then you actually did an error. The fact that you had a sign error is what usually goes wrong. Okay, so let's do Another example. Let's say problem number 24. Square root of x plus 2x equals 1. Okay, so the first thing to do is to isolate the radical on one side of your equation. And so let's subtract 2x from both sides of my equation in order to isolate the radical on one side of my equation. So the square root of x is equal to 1 minus 2x. So don't square both sides of your equation until you've isolated the radical. So now that I've isolated the radical, I can take the square root of x and square it. So that just gives me x. And by the special product formula, I get the following on the other side of my equation. Subtract that's not going to work because you don't know that yet. Okay, let's do problem number 28. Let's see. Oh, wait. I made an error. That's 24. That's 4x squared. Okay, subtract x from both sides. So I get 4x squared minus 5x plus 1 is 0. Oh, I can factor this. Okay, so this just factors into 4x minus 1. X minus 1 is equal to 0. So let's set each of these factors equal to 0 and solve for x. So either x is equal to 1/4 or x is equal to 1. So let's check. So let's check. X equals 1/4. So I have the square root of x plus 2 times x. Is that equal to 1? Is a half plus a half equal to 1? Yes. So 1/4 is a solution. Let's check. X equals 1. And so is the square root of 1 plus 1 plus 2 times 1 equal to 1. So is 1 plus 2 equal to 1? No. And so this is not a solution. So I only have one solution, the 1/4. But notice if I change the sign of the square root to a -1, then that would have worked. And so I suspect that I've done everything correctly. So let's do another example. Let's do problem number, let's say 34. Oops. So problem number 34. The square root of 4x minus 3 plus the square root of 2x plus 3 equal to 6. So notice in this case, the square root is not isolated on one side of my equation. So let's bring one of the square roots over. Let's bring the square root over so that the square root I'm isolating is the more difficult square root. So let's isolate radical 4x minus 3 on one side of my equation and bring the other radical to the other side of the equation. But notice that, unfortunately, this means that one radical is isolated, but not the other one. So I've only isolated one of the radicals. But no matter what you do, you can only isolate one of the radicals. And so what this means is that I'm going to have to use this technique twice. Once to get rid of one radical and another time to get rid of the other radical. So just have to do this. So square both sides of my equation. The square gets rid of the square root. And luckily, we remember the special product formula. So 6 squared is 36. 6 times the radical times 2 is a negative 12 radical. The radical squared, the square gets rid of the radical. Combine like terms. So I get a 2x plus 39 minus 12 radical, 2x plus 3. Subtract 2x from both sides of your equation. Subtract 39 from both sides of your equation. Divide both sides of your equation by 2. And now, square both sides of your equation to get rid of the radical. So now you notice that when you square both sides of your equation, the radical will disappear in this case. And so I have x squared, again, remember your special product formulas, minus 42x plus 441 is equal to 6 squared is 36 times 2x plus 3. Let's multiply the 36 inside the parentheses. And so I get x squared minus 42x plus 441 equals 72x plus 108. Subtract 72x from both sides of your equation. Subtract 104 from both sides of your equation. Factor. Set each factor to 0. And solve for x. So x is 111, or x is equal to 3. So I've got to check this. And so I have, is the square root of, this is problem 34, 4 times 111 minus 3 plus square root 2 times 1, 1, 1, plus 3. Is this equal to 6? Okay, so square root of 444 minus 3 plus 222 plus 3. Is that equal to 6? So 441 plus 225. So is 21 plus 15 equal to 6? No, but luckily, if you switch one of the signs of one of the radicals, it actually is correct. 21 minus 15 is 6. So I suspect we didn't do any error. So this is a solution. Let's check 3. So let's plug in x equal 3 here. And so is the square root of 4 times 3 minus 3 plus 2 times 3 plus 3 equal to 6. Okay, so let's check that. And so 12 minus 3 is 9. 6 plus 3 is 9. 3 plus 3 is indeed equal to 6. Therefore, x is equal to 3. And so in this case, there's one solution. Let me do problem number 64. Square root Oh, actually, let's do 62 because let's do 62. Cube root cube root 8x cubed plus 4 equal 2x. So the cube root is already isolated. So let's cube both sides of my equation to get rid of the cube root. So I get 8x cubed plus 4 is equal to 8x cubed. And so 4 equals 0. So in this case, there is no solution. Darn. Okay. Let me do another cube root. Let's do problem number 61. Let's do problem 61. The cube root of 2x over 3 minus 1 is equal to 1. So let's cube both sides of my equation. So 2x over 3 minus, add 1 to both sides of your equation. Cross multiply. Divide by 2. But since it is a cube root, I have to check for even roots. As long as I do not suspect I've done any error, then I do not need to check. You are only required to check if there are even roots. So only for radical equations that involve even roots. So in this case, x is 3. So I'm done. Okay, so that finishes off section 10.6. Let me go on to section 10.7, which are complex numbers. So earlier today, I said, well, you couldn't take square roots or even roots of negative numbers. Now you're going to be able to. So complex numbers. So recall, if I had x squared plus 1 equals 0, then I try to take the square root of a negative number, and well, I can't do this for real numbers, so can't solve this. If x were a real number. So I have to somehow introduce something else so I can actually be able to solve things of this type, because I want to be able to eventually solve all at least quadratic equations. And eventually I want to be able to solve all polynomial equations. And so we would need to introduce this new idea, the new field, complex numbers. Complex numbers. So I'm going to introduce this where I don't sort of take as a basis that the square root of -1 makes sense. So I'm just going to introduce this a slightly different way. So the complex numbers will be a Cartesian product of the real numbers. So with the following algebraic concepts. So I'll define addition of two complex numbers as follows. I'm assuming that A and B are real, and C and D are real. Then to add these two complex numbers, I'll just add the real parts and add the imaginary parts. To multiply, I'll do A times C minus B times D, and then AD plus BC. Additive identity will be 0, 0. The additive inverse will be minus A minus B. The multiplicative identity will be 1, 0. And the multiplicative inverse of AB, I'm assuming it's not going to be 0, 0. The multiplicative inverse will be the ordered pair A, or A squared plus B squared, minus B, or A squared plus B squared. Okay. So, note the following. If I multiply these numbers together, I get 0 times 0 minus 1 times 1, comma, 0 times 1 plus, well, 1 times 0. So that's 0 minus 1 is a negative 1. And 0 times 1 is 0, plus 1 times 0 is 0, 0 plus 0 is 0. So, let me give you some notation. I'll write AB is A plus BI. So what I've just written here is the fact that I squared is negative 1. So with all this sort of abstractness here, this says that I squared is negative 1. So I can think of I as just being the square root of negative 1. Okay. We usually write a complex number as a real part and an imaginary part. Notice that the imaginary part is still a real number. So we usually think of C as consisting of numbers of the form A plus BI, where A is a real number and B is a real number. Okay. And where I squared is negative 1. Note I to the 0 is 1. I to the first is I. I squared is negative 1. I cubed is I times I squared, so negative I. I to the fourth is, well, the square of I squared And so that's just going to be a positive 1. I to the 5th is, well, I times I to the 4th. I to the 6th is I times I to the 5th. I to the 7th is I times I to the 6th. I to the 8th, 1. I to the 9, I to the 10, negative 1. I 11, negative I, etc. Continuing with the same pattern. And so we get that I to the n is equal to one if n mod 4 is 0, I if n mod 4 is 1, negative 1 if n mod 4 is 2, and negative I if n mod 4 is 3. So let me give you modulo. And so n mod k is the remainder of n divided by k. So if you divide these, it's whatever the remainder is. Okay. So in this case, if you do 9 divided by 4, the remainder is 1. So 9 mod 4 is 1. So I to the 9th would equal I, because 9 mod 4 is 1. Okay, so let's do some examples. And let's say on page 407. Okay, page 407. Let's do problem number 5. Problem number 6. I to the 13th. Well, I to the 13 is equal to I to the 12th times I to the 1st. And so this is just I to the 4th cubed times I. But I to the 4th, well, I squared is negative 1, and negative 1 squared is 1, so I to the 4th is 1. 1 cubed is 1, so this is just I. Or you can think 12 divided by 4, 13 divided by 4 is something with a remainder of 1. And so I to the 13 is the same as I to the 1st, which is I. Let me do problem number 14. Square root of negative 18. And so the square root of negative 18 is the square root of negative 9 times 2. The square root of negative 9 is 3i, because you're taking the square root of a negative number. Square root of 2 as well, just the square root of 2. And so your final answer is 3i rad 2. Let me do problem number 25. Eight plus 5i minus 6 plus 2i. Okay, so all that sort of abstraction just says that the way that you add, multiply, etc., divide is the same way you've always done. You just use the fact that I squared is -1. Okay, so this is just 8 plus 5i minus 6 minus 2i. 8 minus 6 is 2. 5i minus 2i is 3i. And that is your answer. Let me do problem number 34. Two plus 4i times -3 plus 8i plus 6 minus 5i. Let's multiply this out. So this is -6 plus 16i minus 12i plus 32i squared plus 6 minus 5i. Combine like terms, 6's cancel. So you get I squared is -1. So 32 times -1 is a -32. 16i minus 12i is 4i, minus 5i is -1i. And that is your answer. Let me do problem number 40. Two radical 5 minus 8i. In exercises 37 through 42, write the conjugate of the complex number and verify. And so the conjugate of a complex number is you just change the sign of the imaginary part. So the minus 8i becomes a plus 8i. That's why we called in the previous section the conjugate, well, that was the conjugate because, well, the complex conjugate is defined in this fashion. So the conjugate that I was talking about previously was named after this complex conjugate. And so it says verify that if you multiply these together, you'll get the sum of the squares of the imaginary and real part. So this is the product of the sum and difference of two terms. And so it's just the difference of their squares. So 2 squared is 4, rad 5 squared is 5. 8 squared is 64, I squared. But I squared is -1. And so this becomes a plus 64. So this is equal to 84. Okay. Let me do problem number 49. Two plus I over 4 minus 5I. In exercises 43 through 50, find the quotient and write your answer in standard form. Okay, so let me multiply and divide by the conjugate of the denominator. Two times 4 is 8, plus 10I, plus 4I, plus 5I squared, over. Product, the sum and difference of two terms. So 4 squared is 16, 5 squared is 25, I squared is -1. And so 8 minus 5 is 3. 10I plus 4I is 14I. 16 plus 25 is 41. And that is your answer. They actually ask us to write it in standard form, 1 plus a 14 over 41I. So if you write it in standard form, it's written as follows. Okay, let me go on to section 10.8, which is on applications. And so Pythagorean's theorem. I can't do that now. Which says that suppose you have a triangle with lengths of sides A, B, and C, then A squared plus B squared equals C squared, if and only F. This is a right triangle. With hypotenuse of length C. So a hypotenuse is the side opposite the right angle. So let's do some examples. Let's say on page 445, let's do problem number 2. In exercises 1 through 16, determine the third side of a right triangle, ABC, whose hypotenuse is AC. Approximate the value to 3 decimal places whenever necessary. So AB is 6 inches. BC is 8 inches. Determine AC. So A squared plus B squared equals C squared. So 6 squared plus 8 squared is C squared. So 36 plus 64 is 100. Therefore, C is 10 inches. And that is your answer. Let me do problem number 9. A ladder is 10 feet long. And leans against the wall. Oh boy, here it is. Okay, it's 10 feet long and leans against the wall. The foot of the ladder is 5 feet from the wall. Approximate to 2 decimal places. How high the top of the ladder is when resting against the wall.